Good evening, everybody, and welcome to tonight's edition of the Triangle Area SQL Server User Group's Advanced DBA meeting. So tonight we have the pleasure of Torsten Strauß, who's going to be talking to us about page latches. And we definitely appreciate you taking the time now that it's Wednesday morning for you. So, and to help keep things going, I'm just going to hand it right off to you. So please take it away, Torsten.
Cool. So thanks, Kevin. Thanks for the invitation and the opportunity to speak about page latches and ways in order to reduce them. So let me share my screen first of all. Maybe, Kevin, it would be great when you can confirm that you can see my screen.
Yeah, screen is up.
Yeah, okay. Maybe before I will start, it is good to have some kind of a short introduction. So as Kevin already mentioned, so my name is Torsten. I'm a consultant, trainer, and speaker working with BP for a very long time. I'm also most valuable professional since a while and specialized in performance tuning. So that is my domain for since several years. So that's me. So, oh, that is a nice effect. Okay. Okay, I hope you can see Management Studio now. At least this is my intention. Okay,
Yes. Yeah, we're able
cool.
to see it. There is one little thing. There's a message that whereby.com is sharing your screen. Yeah, thank you.
Yeah, okay, great. Okay, let's talk about Pagelet Contention. And I mean, we will see what Pagelet Contention is about, what or why it is often a bottleneck in especially OLTP systems when you have concurrent workload. But I mean, there are some recommendations from Microsoft which you can find in the official documentation. You can see the link here. I do not want to open this because most of the methods Microsoft recommended are already listed here. Honestly, I mean, I do not want to say that they are not working, but I guess they are. Yeah, I mean, they are some of the recommendations are okay. Some of the recommendations are very good. Some of the recommendations, I would say, it is very hard to implement in I would say in a database or even changing the code afterwards. And honestly, some of them, I really have some doubts whether it can reduce page latch contention, at least, I would say, in a way that you can see some kind of a performance improvement. Yeah. So that is the reason why I started my own investigation in order to demonstrate, first of all, what is page latch contention. And then also, I will show some solutions in order to reduce page latch contention or completely eliminate page latch contention. So in order to demonstrate page latch contention, I'm going to create a database, as you can see here. There is, I would say, you know how to create a database. The database is called test. There's one specific thing about the database. You can see we have one file group here, which is memory optimized. That means I'm using the database later on for in-memory OLTP, but for now, I would say page latch contention and ways to resolve page latch contention has nothing to do with in-memory until I use in-memory OLTP, right? So do not mix it up. So the reason why we will see page latch contention and also the solutions are not there because I implemented it in memory OLTP database. Again, this is just a way to demonstrate later on how completely eliminate page latch contention. And I do not want to create another database. That's the reason why we have an in-memory OLTP database here. So let me create this one. So now we have a database, very small one, but I guess should be sufficient. It is running in simple pseudo mode anyway. I mean, when you do not do a full backup in the very first beginning, it doesn't matter in which kind of recovery model your database is running. So it is always sort of simple, but to be explicit, you can see I set the recovery model to simple. So I'm also going to create an extended event. I'm pretty sure you're familiar with the I would say with the architecture and I would say the purpose of extended events. So I will demonstrate later on what we will capture with the extended event. So first of all, I will create this one. Honestly, this is a little bit annoying sometimes. Yeah, okay, that works better for me. In order to make the extended event running, I have to replace a database ID. Sometimes this time it is the same database ID. You can see it's still 17, yeah, as you can see here. Otherwise, the extended event will not work correctly, and we will not see any kind of hard splits, yeah, hard page splits later on. That is the reason why I need to check the database ID. So, and again, this is just about preparation. So what we have done so far, we just set up a database called test, which have the capability to host in memory OLTP tables, right? And we also created an extended event session, which is able to capture hard page splits, as we will see later on. So that's all. Yeah. Now we will start with our journey. And you can see that, I mean, the journey always starts with the simplest object you can create in a database, which is a heap. And there's nothing wrong or bad with a heap. Sometimes it is definitely the solution you're looking for, because as we will see, heap or the structure of a heap is completely different to an index or even a cluster table, which is also an index. So you have a balance tree in between, which created in the background. A heap is just unsorted. So, and it is very likely that a heap does not suffer from page latches, at least not in the same way as cluster tables, because we will see page latches on a heap for sure, but it is reduced, as we will see, because a heap is unsorted. Therefore, we do not have something which is called Pagelet Contention on the, I would say, on the rightmost leaf page, yeah, index page, as we will see later on. So let's start with a heap, and I will give you some explanation what we are going to do here. So you can see we have a table test created here. We have an ever increasing key. Yeah, so you can see it here as an integer with a property identity. So the identity is always bigger than the one which was inserted before, right? So when I'm now inserting 200 records in an explicit transaction just for performance reasons, otherwise you're running in implicit transactions, you have a commit every time, every loop, every iteration. So it is much better to have it in an explicit transaction outside the loop. So, but this is just about performance tuning. So we have 200 records inserted into the heap. And there's one undocumented, I would say, function, which is called fn fizlog cracker. I do not know whether other parameter values exist than fizlog. I have no idea, but at least this will give me an idea about the current allocation of the inserted records. You can see we have a file ID. Yeah, so finally, we are inserting our records into a page. And the page is nothing else than an 8 kilobyte, I would say, portion in your MDF and also in your buffer structure, which has an address. It is a file ID, it is a page ID, and it has a slot. Yeah, so within the page ID there's a slot, which is the so-called raw offset array, which tells SQL Server where to read as a record. What is the offset, right? And we have, with this function, we get a very, I would say, very handy view, and you can see that most of the, or not most, every, I would say, seven records, all of them will or can be saved within one page, and then a new page starts. Yeah? So because the page becomes full. But nevertheless, you can see that because of the way we inserted records, so we inserted a record in a single threaded workload, and by chance, really just by chance, the IDs we inserted are also aligned with the page IDs. That means it looks like they're inserted into an orderly manner, but this is not guaranteed. Yeah. So if you really want to have an ordered ID, which is aligned with the page ID, you have to go with an index. That is the idea of a balance tree. Yeah, Microsoft SQL Server is forced to insert the records, as we will see later on. Yeah, I would say in the sort order of the index key, right? So anyway, we can see that we have a lot of records here, 200s, yeah, because we inserted 200s, not very surprising. And we have the page ID, we have the slot ID, and we have finally the ID, which is the ever-increasing key. So I just want to give you some idea how it looks like from a page perspective. So now I'm going to truncate the table, and I will start to first of all, open Windows Admin Center, which is a nice replacement of these kind of really ugly. Now I have to go to, yeah, it's a nice replacement of the ugly performance counter, yeah, perfmon. I'm pretty sure all of you know perfmon because this is a very, very old tool, yeah. And I mean, I really like the Windows Admin Center when you are able to set it up. Sometimes it is not very easy because of certificates. Nevertheless, it is definitely worth to give it a try and spend some time in order to make it work. Yeah. So what I have done here is there is one object which is our database, right? Or to be very precise, this is our server. We have an instance. There's a performance counter of an instance which is wait in progress, and the counter is Pagelet waits. Yeah. So currently nothing is going on my SQL Server. That is the reason why we cannot see anything here. Yeah. So the Pagelet is, yeah, I would say 0. And we can see, I mean, yeah, privilege time, processor time, user time, CPU time is also, I would say, neglectable. Yeah. So that's it. But we will see when we run the workload the first time that that SQL Server run into page latches. And you have to understand that the execution time of a workload is nothing else than wait time plus CPU time. So when you wait a very long time for I would say, for a specific workload, you have to identify why you're waiting. Is it because of wait types, specific wait types, as we will see here, or is this because of CPU? There's a big difference because often you have, I would say, you have to consider the overall workload and not just one query, because the overall workload can suffer from, I would say, resources. Yeah, and when the resources aren't available, the query has to wait. So you cannot just tune one query because then your query might be fast, but other queries have to wait for the resource, right? And that is something you really have to think about. What is execution time? Again, it is CPU time plus waiting time. And currently there are more than 1,000 different reasons why SQL Server has to wait. And one wait statistic is page latch. And we will talk about page latches in a moment. But first of all, I want to run the workload that we can see something. I can demonstrate something, and then we can talk about the reason why we see page latches. So let me go back to my management studio. So I will use OStress. I'm pretty sure most of you use and at least know OStress. So when you really want to do some performance tuning, well, first of all, you want to understand how your database will scale. Yeah, when you run a workload, the only way to do it is use OStress. So let me go back to the command. I just want briefly give you an explanation. So OStress is a tool which comes with RML utilities. I think it is now renamed to Database Experience Pack, or I don't know the name anymore. Just Google for OStress, you will find it. It's for free. It's from Microsoft. I think it is even what is it, installed with SQL Server 2019. I'm just Google for it. And so you connect to your instance, to your database. So -d is a database, -s is the instance, right? And then you can either use an SQL file, or you can run a specific command. You can see what I'm doing. I'm inserting into the table the default value, which is the ever-increasing identity, which means every record I'm going to insert is, or the counter is bigger than the former inserted default value for the ID. So you can see I'm doing it. So this is R 1,000 times on 400 different threads. And that is what you really have to do when you think about performance tuning. Yeah? It isn't, you're not alone on your SQL Server. There is always something going on your SQL Server. The more users running the same workload at the same time, the more difficult it becomes to tune a server, because often it will not scale anymore. So that is a way to simulate concurrency and running the same workload across several threads. And you can easily start this by CMD. Often it is better to run it as an administrator, because then you have all the permissions you need. And now, before I just want to give you an or the other way around. What I'm doing when I run the script, and it only lasts for 10 seconds, as you can see. That is the reason why I want to explain at least the second script and also the third script, because I'm running them during the 10 seconds. So here you can see I'm running the script within a loop, and I'm looking for current wait statistics, waiting task. And whenever the wait type is page latch, something which is shared, which is update, which is exclusive, I mean, these are the most common page latches, it will automatically stop. That is the first one, or the first iteration. And I'm trying to capture page latch on a PFS page, so page free space page. We will talk about page latches, PFS pages in a moment, but I just want to give you some understanding what I'm going to do. So I'm trying to capture a page latch which happens on the PFS page, as you can see here, but it is not guaranteed, because my SQL Server, my PC, is really fast, and the reason why it is very likely to see a page latch on the data page and not on the PFS page is because I'm inserting a record which already have some filler. That means there is a block on the data page and not on the PFS page anymore. It is not really something which I can capture. I cannot guarantee this. So let me execute this one. So again, it only takes 10 seconds. I have to be fast. So yes, we have a lot of them, and I will skip this one. So sometimes we will see a page latch on PFS page, sometimes not. But you can see that at the moment I'm running this statement, I'm running the insert statement 1,000 times on 400 concurrent threads. You can see that the current wait situation is SQL Server have to wait for a page latch exclusive, and maybe we will also see a shared. No, not. I mean, this was a snapshot. When I'm doing the same exercise another time, it is likely that we will see a shared page latch as well. But the reason why we always see an exclusive page latch is because an exclusive page latch is not compatible with another exclusive page latch, right? So, and that is once you have one exclusive page latch on a specific page, and another thread would like to get and first of all to read and insert data into the same page, it also ask for an exclusive page latch. And that is the reason why you have these kind of queue. The first exclusive page latch will force a queue. And now we will talk a little bit about what is a page latch. So I will dump one of the page. We'll take, I don't know, it really doesn't matter. So you can see the first, I don't know, 13 threads are, I would say, competing for this resource. And the resource is nothing else than the database, which is 17, which is my database test. Then we have a file ID, so my current setup or the architecture of the test database. only have one primary file and logically also one primary file group. So we have only one file. And then this is a page, 8 kilobyte big, that's it. And now SQL Server want to insert records into the same page in concurrency. And this doesn't work. And I will tell you why. Let me first of all dump one of the page. And by the way, we can also see the allocated weight statistics. And we can see that we have Pagelet exclusive in the top 5. And to be honest, something which is named idle and sleeping is something which is good. It is not bad. So I really like to sleep and I really like to be idle. So that is a reason why it is not on position 5. It is even on position 3. Yeah. So that is one way to look afterwards, using DMO's weight stats in order to get a feeling. Do you suffer or no, do SQL Server suffers from page latches? Yes, in our case, that's true. So I will dump one of the pages, which I took from the result. And you can see this is nothing else than the EBCC page command, which give me a very nice, I would say, translation of the hexadecimal code. I mean, it is nothing else than the so-called variable fixed format. So this is a format here, but what is the most, in terms of page latches, the most important information is something which you will find here. And what you will find here, by the way, this is just the buffer address. So this is the page. So we can see the page header, which is 96 bytes big, always 96 bytes. There's only one difference when you work with page compression, but I'm not going to introduce the so-called column description format. This is about the normal uncompressed page. So we have the page header here, which is 96 bytes long, as already mentioned. It stops, to be honest, it stops here because these are the metadata. And there's one very, very important information, which is called M3 data. So M3 data tells SQL Server, to be very precise, the thread where to insert the next record into the payload. You can see this is my payload. Now consider the following. The first time SQL Server wants to insert the very first record into the heap, it will allocate a page. Perfect. And then it will insert the first record at position 96 or 97, which is the first byte after the header, because the header is always, I would say, some kind of safe. You cannot overwrite the header. So, and once this is, so first of all, SQL Server has to read the position where to insert the record. 96, or in our case, the next page or the next record will be inserted at position, it's called the offset 7173. So it has to read the information. That means SQL Server have to latch the page with a so-called shared page latch. So a shared page latch is compatible with any kind of other page latch, but not with the exclusive page latch. That means several threads can read the same information. Now the first thread will insert the record into the page, starting with this offset. In order to avoid that another thread is going to insert the same information at the same position within the page, SQL Server has to latch the page exclusively, because otherwise we will end up in a so-called lost update issue. So one thread will overwrite the record which was inserted by the other thread. That is the reason why SQL Server have to latch a page exclusively when it have to insert, update, or delete records within a page. Once the exclusive page latch is gone, SQL Server can now release the page latch, and another thread can insert the information in the updated or after, how can I say it? So the offset, the position is already updated by the former insert. So the new thread will read the information where to insert the record. Yeah? And that is, so in this way, SQL Server will not overwrite the already inserted records. Okay, that is the idea, and it is, yeah, that is the idea and the need of a page latch. Without page latches, nothing will work. That is the reason why it is very, very hard to eliminate page latches or reduce page latches, because you understand that page latches is not comparable with a transaction where you have a lock and a block, right? This you can definitely, I would say, for your read operation, you can determine the duration for your shared latch, not for your exclusive latch, but for your shared latch. That is nothing which I can do here. SQL Server has to determine the duration of the page latch. And the only way in order to, I would say, fasten the process of acquiring and releasing a page latch is to have faster CPUs, not more, because when you have more, you are running into more concurrency. That will even, I would say, have a negative effect here. So, okay, that is about page latches. At least some kind of a rough understanding, yeah. So rough explanation from my end. What we can see now is there's one DMV which is called DMDB database page allocation. So in former times, I think SQL Server 2014 and before, hopefully no one is using SQL Server 14 anymore because of outdated support and other reasons. There was a DBCC function which was called DBEND, I guess. So this is now replaced by a very, I would say, handy DMV and also fully documented by Microsoft. Yeah. So you can see that we are getting all the pages here. We can see we have, by the way, we have almost, we have roughly 57,000 rows. So every row is one page. Every page is 8 kilobyte big, right? So just to give you a better understanding. And we can see that we have some information about the free space page. Yeah. So that is the physical fragmentation of a heap, but you do not have any kind of logical fragmentation, because logical fragmentation will not work when you have a heap, because a heap is unsorted, right? So you can see that the physical fragmentation is pretty nice. Most of the pages, in the end, you will see some of the pages which have maybe 50% of page allocation, but all the others, I would say 99% of, you can see here, 99% of all other pages are almost full. There's a PFS algorithm in place. You cannot even make a page full by 100%. That doesn't work. Yeah. So is this, sorry, there's a question?
Yes, a question just came in and might need a little bit of back and forth to help get it clarified, because the question is,
sure.
Would a page latch be successful if the resource is in a state of deadlock?
When you run into a deadlock, you know that you have a victim. So SQL Server will automatically roll back the transaction. So normally the operation, which is the cheapest one. So a deadlock is caused by a transaction, so by locking and blocking. This has nothing to do with latches. Latches is an implementation, so it is a protection of a physical internal structure, which is in our case a page. It is a good question, and it is very good example that, and I do not misunderstand me, that it was also my problem. It is hard not to mix up a latch and a lock and a block, right? A latch is really something which happens on a physical structure, which is a page. A lock and a blocking is just because we want to have an asset control. Yeah, atomic, consistently, isolated, durable. So C and I, this is of asset, this is transaction. So if you're running into a deadlock, yeah, so this has nothing to do with a page latch. Okay.
Great, thank you.
Yeah. but feel free to ask. I know it is not a very easy topic. So what you can see here is I'm asking SQL Server about the page allocation, or the space allocation, which is a page allocation. But you can see this is maybe I need, sometimes it's a little bit bigger, sometimes it's a little bit smaller, depending on the workload. But you can see this is roughly 460 megabytes, I would say. Yeah. So we can even break it down by different pages. And you can see we have data pages, we have one IRM page, that's all. I mean, this is a complete different story when we go into a balance tree, because we have a data page, we have intermediate level, we have root pages, we have leaf pages, a complete different story. Yeah. So I just want to visualize that, I would say, how it looks like from a page allocation and also from a sizing perspective. So I do not want to go into the transaction log. This was just an idea, but I didn't find time to finalize this one. So, okay, what we understood so far is that even in a heap, we have page latches. Surprising, because people think that page latches always are, or the root cause of page latches the B tree. Yeah, the index B tree. Yeah, that is not true. Okay, so let's talk about a B tree. So we are creating the same table another time, but this time it's exactly the same table so far. But now I'm adding a constraint, a primary key clustered, based on the ID. That means we have a last page insert contention. When you think about a balance tree, and I'm pretty sure you know how a balance tree looks like, SQL Server now have to insert the data into the rightmost page within the leaf level, because SQL Server is forced to insert into in an ordered fashion, and therefore it always has to read and insert into the rightmost page on the leaf level of our balance tree. SQL Server has no chance to do anything else than that. And that is a problem. That is a problem what you always see, even, I would say, the performance impact, as we will see, is dramatic comparing to a heap. Because in a heap, SQL Server can decide where to insert the record. It does not have to worry about in order. But in a balance tree, SQL Server have to insert in an ordered fashion, based on your index column, which is in our case the ever increasing key, which is the column ID. So, and you think about, you have a customer number, so it is very likely that you have an identity, because a customer number is nothing, is a business key. Yeah. So next customer, I don't know, if you're an Amazon customer, you get your customer number 1. Next customer is customer 2. It is just a number, right? But it is ever increasing. So let me make this happen. So perfect. Now we have our primary key. So that means the table is not a heap anymore. We have a cluster table. So I'm going to insert the same amount of records another time, 200 records, just to give you an example how SQL Server will insert the records. So you remember the undocumented function, which we used in the very first beginning. By chance in heap, it was also ordered, but just because of the way we inserted data, there is no guarantee when I'm now inserting data into a heap another time. So there is no guarantee that it is ordered. And when we are running, as we did in a concurrent workload, it cannot be ordered anymore. Here, SQL Server have to force the order. You can see here we have a guarantee that every page in the ID is always ever increasing. You can see it here. It's perfectly ordered, and it is when you see the index physical stats now, it is a perfect index, no logical nor physical fragmentation. Okay, but this will change, as we will see. So I will truncate the table. And this time I'm starting the extended event session, which we set up in the very first beginning. This is able to capture hard page splits. Do not use performance counter in order to figure out your page splits. There are two different types of page splits, soft and hard. Soft means SQL Server have to get a new page because the last page becomes full. Okay, that's normal. I mean, this is also true for a heap. So the problem with a performance counter page split is that the performance counter will capture soft and hard page splits. You cannot distinguish between both types. The only way to do it is with an extended event, as we set up in the very first beginning. You have to read the transaction log for a specific event. And here you can see that you're running into hard page splits. That is what I need to worry about, not soft page splits. I cannot do anything about soft page splits. The only way to reduce it a little bit is to make sure that I have maybe row compression, page compression, and I choose the right data types, right? Because then it is very likely that I can have more information in one page. That is the reason why SQL Server does not need to have that many pages, yeah, to save the same amount of information. So I will start this one. And pages is already on. Yeah, so fine. Oh, I didn't reveal the page latches for the heap, but we will do it now. So where's my mouse? Okay, that's strange. My mouse is back. No, it's not here anymore. Ah, great. My mouse is gone. Oh, that's nice. This is what I like. Okay, let's try to do it with a cursor. Okay. I've never ever experienced that my mouse is not working anymore. At least the mouse pointer is not working. But okay, I will give my best. So I'm running the same workload as before, 1000 times, 400 threads. And I will go to, this is a little bit strange anyway. So we can see that my mouse is not there anymore. 1 second, I need to find my mouse. Not there anymore. This is so strange. I do not want to restart my PC. Sorry for that. Nothing which I can foresee, to be honest. Okay, now the things becomes a little bit more difficult for me because I need to scroll. And okay. This is super annoying now. Okay, maybe it works with tabs. You can see that here the page latches. So I was running the same loop another time to detect page latches, and we can see the same not the same, but we can see a resource description here. And this is one of the resource description. You can see this is just another data page. Yeah, same file, same database. So I will copy this one. And by the way, we can definitely look for the accumulated weight statistics, and you can see position 2 and 3. This is about page latches, so it looks different. So we can see we have more page latches than before, right? Comparing to the former example. By the way, the recorded page latches in my example, so the documented one, and nothing I can foresee. Sometimes it is more, sometimes it is less. So do not worry about this one. It has to be different. Yeah? So depending on a lot of things, I cannot influence. So, but what we can see here is, so first of all, we can do the comparison in terms of time. That is something I forgot. So this time it took 23 seconds before. This is super annoying that my mouse is not working anymore. Let me go to the other example. So the heap, it took 10 seconds just to compare it already. Heap, same workload, 10 seconds. Cluster table, same workload, 23 seconds. Yeah. Why is my mouse gone? Okay. Anyway, I will ask the extended event session now for the number of hard page splits. And yeah, sorry for missing the mouse, but it's harder for me than for you, I guess. So you can see the number of page splits is almost, or roughly 83,000 page splits. Now you need to think why. Because we are running 400 concurrent threads. And SQL Server is forced to insert in an ordered fashion. There is, the first thread will get an identity, which is 1. The second get an identity, which is 2. 400 threads will get an identity from 1 to 400, but there is no guarantee that the first thread is the first thread which can insert the record into the balance tree, right? That is the reason why we run into physical page splits. And that is what we can see here. We have 83,000 page splits. A page split is a horrible, expensive operation. All these kind of things are fully locked in our transaction log, for example. SQL Server have to get a new page, roughly 50% of the data which is in the page where SQL Server have to insert the record into the ordered fashion will go to the new allocated page. This is the page split. Then SQL Server have to correct the so-called doubly linked chain on the leaf and also on the intermediate level and so forth. Horribly expensive. So, and this is what we can see here. And this is also one of the reasons why it took so much longer. 23 seconds instead of 10 seconds. So I will dump. I cannot. I can. I hope I have it still. Yes. So this one was one of the page. Okay, cool. Now we are back. So the session is already stopped, I guess. Yeah. Okay, cool. Okay, so, and this was one of the pages, and my mouse is back. Cool. So what we can see here, and this was a little bit surprising for me, the M type, this is another information in the header. This will tell you, or SQL Server, it is an index page. This is not a data page. You know that when you think about the clustered table, the leaf of the B tree is a data page, not an index page. The index page, where we can see a lot of page latches, is the intermediate level. And that makes sense because SQL Server have to read the intermediate level and have to update the intermediate level when it have to insert record in the rightmost page. That is the reason why the intermediate level page becomes your bottleneck. It is not just your leaf, your rightmost leaf page, it is also the intermediate level. So this is more likely to see page latches on the index pages rather than on your leaf or data pages. That was something I didn't know. So now I know it, and now hopefully you know it as well. So what we can see here is from an index perspective. So we can see, first of all, we have all the pages which are allocated, and you can see I have a marker here, which is very easy because we have a doubly linked chain. So if the doubly linked chain is not aligned, so it is not +1 or -1, we have a logical fragmentation. That is just another way to look and also reveal logical fragmentation. So we can see wherever you can see a 1 here, we are running out of, or the physical order of the pages is not aligned with the logical order of the index key. That is the logical fragmentation. And the logical fragmentation is caused by the physical fragmentation, which is caused by the page split, by the hard page split to be very precise. So let me go down here and we can see the same information by the index physical stat. You can see the average fragmentation in percent, so the logical one or the external one is 94%, and the physical one or the internal one is 57%. That means almost every second page is completely out of order. The physical order is not aligned with the logical order. Now think about read ahead mechanism in SQL Server. It will not work anymore. So that means read ahead is completely, I would say, out. How can I say? It is not considered from SQL Server anymore because of the high fragmentation. People always forgot about. People always ask me, okay, we have SSDs now. We have them in memory when we read it. When we read the data first, that's true. But the read ahead mechanism is not working when your index is heavily fragmented, and that really causes also a lot of performance problems. Let me go to the what is it? The space allocation. Yeah. So it is more than before. Why? Because of the page splits and because of the reason that in average a page is only half full. That is the reason why we need more pages. When we need more pages, we need more space. So another reason why you need to consider, why you need to think about how we can reduce Pagelet contention, because this is the reason for all the problems we have seen so far. So you can see how it is a breakdown, not very important to be honest when you understand it once. So this is nothing I want to introduce. I just want to tell you the outcome. So people are always telling me use a sequence instead of an identity, which is faster. No, it isn't. Even if you do it right, because there are recommendations in order to for the caching of the. Where's my sequence, by the way? Here, the caching of the sequence. Yeah, so there's a very interesting article from Itzig Ben Gan. Definitely recommend, or everything he writes is recommended, yeah, to read. But I mean, I also did my own, I would say, experience here and different findings. So I was trying with different cache size. It has no impact anymore because there was how can I say, an improvement in SQL Server 2017, at least 2019, where an integer is also cached. Yeah? So there is no difference in terms of identity and caching anymore, maybe in some edge cases. But I mean, sequence have other, I would say, benefits. You can get the next value from a sequence, which is very, very handy. You can reserve them. There are a lot of other things you can do. Yeah, comparing to identity. Identity is very dumb, I would say. Yeah. Nevertheless, the outcome is, yeah, that is running the same workload with a sequence. It's, yeah, comparing with the identity. It's, I mean, nothing. Yeah. So do not worry about sequences in the identity. Again, edge cases. Yeah. Okay, so now we want to resolve it. How can we resolve page latches? You understand the reason is that there's a concurrency of there's a concurrency. Well, 400 different threads are competing for the rightmost page. That is why we can see page latches. So taking this into consideration, we have several ways in order to resolve it. So first of all, we can create a hash partition. As always, I'm running out of time. That is the reason why I think I do not want to execute every single statement anymore, but I want to tell you what you need to do and also what is the output. Okay, so the idea is we will create a hash partition. How can we create a hash partition? We can create a partition function. Yeah, we call it hash, and it accepts and also expect a tiny int, right? We can see that we have 10. To be very precise, we have even 11, yeah, because there's always one partition to capture everything which fall outside the range. Yeah. So we have 11 partitions, right? And we can also create a partition scheme. I mean, most people know how to create a partition function, partition scheme, which is using the newly created partition hash. So that's it. So when we have this in place, we can use, we can implement something like this. We will create the same table as before. We also use an identity, but we will also create a hash value. And the hash value is nothing else than a modulo of 10. You can see it here, modulo of 10. And because we are using the hash value in our hash function, in our partition function, which is the hash function, by the way, SQL Server will now spread across different partitions. That means the concurrency is already in average reduced by the factor of 10. Because what you will do is you are creating an aligned index, right? So you can see it here, which takes all, otherwise it will not work here. Yeah, you have to insert the hash, the partition function key into the unique index. So that is the only way you do it. And by the way, then you have a so-called aligned index, right? And now that means the first record will go into the first partition. The second record, so this, to be very precise, is the value of 2 will go into the second partition, the value of 3 to the third, and so forth. When the 11th value is there, this one will go to the first partition. That means, in terms of concurrency, I'm already able to reduce the likelihood that we are running into a competition by the factor of 10, because we will end up with 10 balance trees. That is something you need to consider. Whenever we have a partition and an aligned index, we do not have just one balance tree. We have, in our cases, 11 balance trees, yeah, because of the empty partition, or the partition which is always there to capture everything which is again is not in the boundary of the defined partitions. So, and that is something which is very, very handy in terms of eliminating or reducing Pagelet contention. Let me go down, down, down. At least I will show you the performance improvement. So before, using the cluster table, it took us 23 seconds. Now we still have a cluster table. We do not have a heap. You remember the heap was 10 seconds. I do not want to blame the heap because it took 10 seconds, and this time it took 9.5 seconds. This is not the idea. But a heap is unsorted. We can never ever have an index seek operation on a heap. That means every single select statement is always a table scan. Here, we use a clustered index in order to seek. And I mean, we are inserting almost 2.5 times 2.5 times faster than before. The problem is, let me go down. The problem is, so we end up with less hard page splits for sure because of less concurrency. We have better index statistics. But the problem here with this one is, so when I now run something like this, select all from test, yeah, and this one is partitioned, and I'm just using the ID, this will always end up with a full partition scan. That means I'm actually I'm accessing 11 partitions, 11 balance trees, which I need to scan, which is horrible slow. So I have a fast insert, but when I'm doing it this way, I have a very, very slow read performance. This is, you always have to find the right balance, right? So what can you do, and what you have to do, you have to add the partition function in your where condition as well, which is not very handy to be honest. But then SQL Server can eliminate all the partitions because it already knows where to find the record, in which partition at least, and we have an index seek. And this is so fast because we reduce the number of pages by a factor of an average 10, because we have 10 concurrent balance trees, but only one needs to be accessed in order to find the value. So that means we have a very, very fast insert performance, but we also have a very, very fast read performance when you do it right. So let me go down. Will you tell you another technique in order to resolve page contention? So there is one which is called the so-called reserved bit. Yeah, okay, that's fine. I get the error message, which is fine because the partition scheme and the partition function wasn't created. Resolved by, I think Oracle has something like this in place. So the idea is the following. I will show you the idea. I will create a function and it will swap the bits, right? So when you have something like 1, it is in binary, it is 00000001. So and the function will reserve it to 1000000. Hopefully this is right. Yeah, 7 times O. So this is the so-called byte swapping. That means 2 is when you use the reserve bit function is not bigger than the 1. Instead, you get a complete different, it's not a randomized value, but you get a different value. So that means when you use this function here, and we use the function for maybe 12 records, if I remember correctly, so we can see the hash value. Yeah? So the hash value is different. Then it is not ever always ever increasing because the bits are swapping or swapped. Yeah. So this is another approach, and I will tell you how to implement this one. You have to create a function, but the function has to be deterministic. That means you have to create the function with schema binding. Otherwise, it will not become deterministic. When it isn't deterministic, you get an error message like this. Computed column reserve bit in the table cannot be persisted because a column is not deterministic. And I want to have it persisted because I do not want to calculate my, I would say, the reserve bit on the fly, because this is, I would say, not very effective, right? So I want to have it persisted, and therefore we have to have a deterministic function. And the only way to create it or create a deterministic function is to call the function or to create the function with schema binding. So now, is there a question?
Yeah, a quick question came in from chat. Would it improve the performance if the number of partitions were increased, or is there a theoretical
very good
limit?
question. Yes, this is a very good question. I was trying to do the same, and there I skipped this one. So here we can see it. I increased by the factor of 10. So in the end, was it here? 1 second. So in the end, I created 100 partitions instead of insert 2. No, it should be here. I did it, believe me, somewhere here. But I'm not able to find that more because so much code. Anyway, so what I did is here, you can see it. So I was adding 90 additional partitions, right? So in the end, we ended up with 100 partitions plus 1. Yeah. So I do not want to mention the 0 partition anymore. So 100 partitions. So, and I did the same test, and you can see the time is always the same. So the problem about this is, and I was thinking the same, so why not having more partitions? Because when you have a modulo which is not 10, it is 100 now, you can have more concurrency. There is no effect, as you can see, right? There's some kind of, I would say, maybe there's even a tipping point where the performance becomes worse. The problem is when you scan your table now, yeah, you remember this example, and your hash partition function is not part of the predicate, you are not scanning 10 balance trees, you are scanning 101 balance trees, and you can already imagine that the read performance, when you do something like this, is definitely worse than having 10. So I would say 10, in my example, was a good choice. Maybe 20 is a little bit faster. You should give it a try. But you can see that there is no proportional performance benefit by adding new partitions. I hope you understand what I'm trying to say. Yeah, we should do this session in German. Then it sounds a little bit smarter, believe me. But I hope you understand me. Okay. So this was a bit. This was a reserve bit. The reserve bit function works similar to. It's not similar to partitioning, but you understand that you can something like it is not randomized, but you do not get an ever increasing key anymore. That means when you think about the balance tree, where to insert the record, it is not always the rightmost page. For sure, you will end up with a lot of more page splits. And honestly, the performance impact, or the performance benefit is even worse than the partitioned one. This is the partitioned, 10 seconds. Now we have 13, 14 seconds. You have a lot of Pagelet shared, but the problem is that you have a lot more page splits. And that is the reason you can see it here on the index statistics. So the index is completely out of order. And because of the page splits, which cause the average, which causes the logical and the physical fragmentation, the performance is even worse. I would say not something you want to use in production. Let's talk about in-memory OLTP. That is my favorite approach. I really like in-memory OLTP. I don't understand why people are not on. This is wrong. I understand why people are not using in-memory OLTP for existing projects. When you start with a new project, I would say yes, there are definitely a lot of use cases where in-memory OLTP is so much faster. So let me do one thing. I will create a memory OLTP table. You remember that the table, the database I created have a memory optimized file group because of this example. That is the only reason why I implemented this upfront. So I'm creating the table here. This is the hash bucket. I did the same with a non-clustered. I call it range index. Microsoft originally called the index range index as well, which is much better than a non-clustered because non-clustered is normally row store index. So I will call them hash and range index. So, but this time I'm using a hash index, which is optimized for seek operations, will not work for ordered, and will not work for range scans because a hash cannot be ordered. So this is something you need to consider before you select the right type here. So anyway, so I created the table. We will reset the weight statistic and we will run the O stress. And we will see, and by the way, I have never ever revealed it. And okay, this is working, by the way. We do not have any page latches in memory OLTP. Why? We do not even have pages. We just have records which are linked by an index. That is the reason why you have to have always at least one index when you have an in-memory OLTP table. You do not have page latches. I do not need to worry to protect them. When you get an update, the former version of the record becomes invalid. There's a begin and end timestamp, right? And a new record will be created and will be added to the index chain. There is no need for logging, blocking, latching in memory OLTP. That is the reason why it is horrible fast. You can see it took 30 seconds. I would like to compare this time series here because otherwise, these the seconds I measured here or I monitored here were what is the right word here? You understand that otherwise I have to correct all the timings. That doesn't work. So we are down to 8 seconds. I mean, hash partitioning is very close, but you remember that you always have to add the hash partition function into the where condition. Nothing I need to do here. I do not even need to create partitions. So I don't have any page latches. There are no page latches, right? At least not from the workload by in-memory OLTP. In-memory OLTP does not have any, or at least the hash index does not have fragmentation. It only tells you whether the index chain is okay or not. You can see the average chain length is 1, perfect. Maximum chain length is 7. It's a perfect aligned index, or not aligned, but it's in perfect shape. So the problem starts when we look into the space allocation. So you cannot use the traditional, buffer descriptor. Instead, you have to use the DMDB XTP, which is heckathon, memory consumers. And you will see that depending on the number of buckets, so every bucket in your hash index, which you predefined, will allocate 8 bytes, whether they're empty or not. That is the reason why we already end up with 4.2 megabytes. And the index, the data itself, also take 430 megabytes. So this, let me do the following. Yes, point is right for US. Yes. So you can see this was what we had before with partitioning, with clustered table, almost the same size every time. Now we have much more, and this is in memory. This means we say your current SQL Server memory allocation is reserved by this schema and data durable table. That means this memory will not go away. It is reserved just for the table. Yeah, that is something you need to consider when you work with in-memory OLTP tables. Yeah. So anyway, so we have a perfect index seek here, index seek operation, without adding anything like a hash partition function or whatever. The problem is that hash partition or hash index cannot be ordered. A hash cannot be ordered. A hash is a hash function, which is deterministic, but you cannot order a hash, right? That will not work. That is the reason why you need to think before, do you want to order or do you want to have a range scan? Then a hash index is the wrong choice. You have to go with a non-clustered range index, right? Because otherwise you always end up with the sort operator and even with parallelism, because your cost is, what is it? 163 already. That is the reason why we are running into parallelism, because my cost threshold for parallelism is set to 50. Yeah, and we are allocating 8. My PC have 8 cores. Yeah. So we have a parallelism of 8 plus the coordinator thread. So 9 threads are allocated just by this query, which isn't good. Yeah. So that is the reason why it's the same example. I do not want to run it. I just want to give you an example or an idea. Where is it? Yep. This is the idea of using a non-clustered. I do need to think about the bucket size upfront, which is sometimes a little bit difficult to estimate. You can correct this since SQL Server 2017, I guess, even without copying and recreating the table. It's very handy now. But anyway, now the performance is the same, index insert performance, but all of them, at least the ascending order. Yeah. Okay, I do not have the tables created, but we have an index scan, we have an index seek. Okay, vice versa doesn't work. Yeah, the scanning doesn't work because we do not have a double link chain. We have only a single link chain. But you can see that whenever you have to have a range in order or whatever, it is likely that it is better to take the non-clustered range index. Last 2 minutes or last 3 minutes, maybe, I just want to talk about the new implementation of Optimize for Sequential Key. So Optimize for Sequential Key was introduced in 2019. I do not know all these kind of features by heart anymore, so too many of them. 1 second. Optimize here. Yes, it's a feature introduced in SQL Server version 2019. And it is some kind of, what can I say? It's definitely improvement. And when you do not want to use hash partitioning, when you do not want to use in-memory OLTP, you only have to say, I want to have a clustered index with optimize for sequential keys on. That means from a coding perspective, when you think about your current application code or database code, you just have to add this, I would say the T-SQL syntax to your existing indexes. Hopefully you have an SSDT or I don't know, at least some kind of a Visual Studio solution should be very easy to do it with a regex expression search or replace or something like that. Then you have to rebuild the indexes for sure, because otherwise optimize for sequential key is not working. Yeah? But when you do it and you run the same workload, you are, I would say 14, 15 seconds. Yeah, it's not fast as in memory OLTP for sure. And but it is okay. It is better than 23 seconds. You remember that was our very first example with a clustered index table or with a clustered table. it is a very good, I would say, compromise, because again, you do not need to change that much, but you will benefit from reduced page latches. Instead, you will see so-called B-tree insert flow control. So the idea here is a little bit, read it and try to understand this. Honestly, it took a while for me to understand how Microsoft was able to introduce this. I mean, it is not that important to understand how they did it. It is more than important to see the benefit. The benefit is there. Code changes are less. And that is why I could definitely recommend this one, because I also tried with more concurrency, less concurrency, single threaded, and a lot of tests. It is never ever worse than not implementing the feature. Yeah, so implementing the feature always have a benefit or no benefit, but no flip side or no performance degradation. So that is something I can tell you, at least from my testing perspective. And that's it. You can see I tested a lot here with optimized for sequential key with different concurrency, different type of inserts and so forth. Single threaded, as already mentioned. So yeah. Any question? If that is the best way to contact me. I do not want to reveal my BP address, my BP email address. That's my personal one. So feel free to reach out to me.